Welcome to the Relay Automation and Protection System course. This program is designed to provide comprehensive, practical foundation in the engineering, installations and commissioning modern protection systems. Specifically, we are focusing on the Easergy P5 protection relays and its application within the secondary circuits. The curriculum is built around the Relay Automation Education stand developed for TTK US. This hardware platform allows to hands-on experience with the P5F30 feeder terminals, providing a realistic environment to explore 230 volts and 24 volts DC auxiliary voltages. Also, digital inputs and current voltage measurement circuits. Specifically, we will examine the main location parameter, which is a crucial component of the device system information. To access or modify the main location, you must navigate to the System Info view, which is located under General menu. While some basic information is visible on the local panel, this is specifically string is most efficiently managed using the setup software tools. The main location is user-defined text string used to identify the broad geographical or physical area where the relay is situated. In professional practice, this field is typically used to record the name of the substation or the building. It works in the conjunction with the sublocation, often used for the specific busbar or bay, and the name of this device to provide the complete identifier address. So why it's important to fill this out correctly? Firstly, the miming display. The information is entered in this field can be configured to appear at the top of the mimic screen on the local LCD display, allowing operation to immediately confirm which part of the plant they are viewing. Secondly, for documentation, this location data is automatically pulled into test reports and commissioning logs, ensuring that maintenance records are tied to the correct physical assets. Thirdly, management. It assists in the centralized management device when multiple relays are connected across the Ethernet networks. The main location is flexible string, but it's primarily intended for administration clarity. Unlike the mode of use or scaling settings found in the same menu, changing the location string is descriptive update and does not impact on the protective logics. Think of the main location like the city field on the postal envelope, while the sublocation is the street name and the device name is the house number. The main location tells you postal system or network system, where are you, and substation the device belongs to. Without it, finding one specific relay in the city-size power grid becomes more difficultly. In a P5 protection relay, the sublocation is user-defined text parameter found in the System Info view of the General menu. It serves as a secondary identifier for the device within the larger electric field network. The sublocation string is used to identify the specific part of the facility or substation where the relay is monitoring the equipment, while the main location typically refers to the building or substation. The sublocation is commonly used to record the specific busbar, feeder, bay, motor, etc. The text entered in the sublocation field is prominently displayed at the top of the mimic screen on the LCD display. This allows operators to quickly verify which specific feeder or busbar they are currently controlling or monitoring. Like other identification strings, this information is included in the test reports and logs, ensuring that data captured by the relay is correctly attributed to the specific physical asset it protects. Sublocation field accepts text strings up to 20 characters. It can be modified using the setup software or through HMI panel. This is a descriptive field intended for identification and management. Changing it doesn't affect the relay protective logic or require a device reboot. If the main location is a street name on delivery address, then sublocation is a flat or apartment number. It tells the delivery driver, the maintenance engineer, exactly which specific door to knock on which large building. In the P5 protection relay, the mode of use, also called EAD mode, is a configurable parameter that switches the device between the standard protective role and specialized states for testing and commissioning. This setting is managed within the system info under General menu. The relay operates in one of the three primary modes. Normal mode, this is a default operating state where the relay performs all its intended protection controls and monitoring functions. In this mode, any detected fault results in actual protective action, such as tripping, a circuit breaker, and all operation counters and maintenance logs. Secondly, test mode. This mode is used to verify a relay logic and physical wiring without the need for actual current voltage injections. Then there's forcing status. The user can manually force the status of any protection stage to start or trip. The physical output activation. Crucially, in the test mode, the relay physically operates its digital outputs. These allow technicians to confirm that the wiring between the relays and circuit breakers is correct and functional. There is our virtual injections. This mode enables to use the simulated voltages and current signals or the playback of the files. To prevent testing procedures from screwing actual maintenance data, certain records, such as a cumulative broken current, are not updated while the device is in this mode. Then there's block mode. This mode provides a safe simulation environment for testing the relay's internal logic. Like test mode, it allows for forcing signals and performance virtual injections to see how the relay's logic responds. The primary defense is that the relay remains frozen regarding its physical outputs. Digital boards will not physically activate, allowing for a full logic test without actually tripping the connected electrical equipment. When the relay is set to the either test or test block mode, the maintenance test LED local panel will flash. Changing the mode of use may require a device reboot. User must ensure that this downtime has no dangerous impact. Modifying the EAD mode generally requires engineering or installer access rights. Think of the mode of use like the settings on newly installed home security system. The normal mode is system being armed. If a door opens, the siren screams. Test mode is like walkthrough test, where you open the door and the siren briefly chips to prove that sensors and sirens are physically connected. Test block mode is like silent simulation. You can look at the control panel to see that this will be triggered of the alarm, but the sirens stay silent so you don't wake the neighbors. In the Easergy P5 protection relay, CS level config refers to the cybersecurity settings that determines how users access the security policies are managed. The relay is manufactured with one or two levels. Basic security, level A. This is the default configuration designed to straightforward local security. Passwords are managed directly through the relay local panels or through software. The accounts uses three fixed accounts: operator level, engineering level, or installer level. It includes simply features like F1 key access, control the physical lock the device, and SCADA access control the prevent remote setting changes. Secondly, advanced security, or level B. This is an optional high security level required for crucial infrastructure. It requires the cybersecurity admin or KA software for central management. It is the only level that fulfills the ESC standards. Logs, unlike the basic levels, it generates detailed security events such as tracking who logged in and when. That can be saved on central server. You can identify the CS level by looking at the 17 character of the relay commercial reference code. A is basic, B at advanced. Think of the basic sales like standard house key. It's simple, you manage yourself. It keeps the doors locked. Advanced settings are like high-tech office badge system. Every time someone enters, it records in central computers. In the protection relay, scaling is the essential process of converting the low-level electrical signals received at the device terminals in the actual high power values presented on the electrical network. It ensures that the relay understands the real-world conditions it is monitoring so that it can perform its metering and protection functions. Scaling is used in three simple forms within the relay. Primary scaling, real-world values although the relay is physically connected to the low power secondary signal, it is designed to display measurements as a primary values. By entering the rate value of your current transformers, CTs, and the voltage transformers, VTs, the relay calculates the actual amps or volts following through the main power lines. Secondary scaling is input signals. This refers to the physical signals actually injected in the relay's rear connectors. There are typical 1 amp or 5 amp for current and 75 volts or 200 volts for voltage. These use specific voltage references such as 22.5 millivolts for current sensors. Per unit scaling or relative values, almost all protection pickup settings uses relative scaling. This expresses a value as such as multiple percentage of the related value. This makes it easier to apply standard protection logic regardless of the specific size of the transformers installed in the particular substations. Why it's necessary? Without correct scaling, the relay cannot see between a normal load and a dangerous fault. For example, if 500:5 ratio CT is used a 4 amp signal, at the relay's terminals actually represents 400 amps on the primary network. Scaling provides the value the relay needs to make this convention in real time. Think of scaling like a scale on the map. If you measure 1 centimeter on the map with a ruler, you need a map's legend to tell you that 1 centimeter actually represents 10 kilometers in the real world. Without the scale, you wouldn't know you have measured a distance, but you wouldn't know if that distance represents a short walk or massive journey. In the protection relay, the CT primary setting is the configuration of the rated primary current of the connected phases, current transformer CTs. This value is critical for the relay to correctly interpret network signals and provide accurate protection and measuring. Setting range for phase CTs, the primary current can be configured between 10 amps and 20 kiloamps. The relay typically displays these measurements in the amps or kiloamps. For example, 300 settings. If you have current transformers with a ratio of 300:5, you must configure the relays with the CT's primary of 300 amps and CT's secondary of 5 amps. The ratio, this tells the relay that every 5 amps it feels at its rear terminals is actually represent 300 amps following through the primary power line. If the relay measures a secondary signal of 3 amps, it uses your settings to calculate the primary value. If protection stage is set to trigger at 300 amps, the relay will trip when the primary current reaches 360 amps. This parameter can be accessed and modified through 3 main interfaces. Firstly, HMI panel for navigating for scaling and in the general menu. Modifying this configuration usually requires engineer level or installer level passwords. You must never use the primary circuits before the CT primary and other scaling settings are properly configured. Failure to do so can result in death, serious injury and equipment damage. To ensure the scaling remains accurate during the fault, the CT must be sized to avoid saturation. For definite time protection, the current must be greater than 1.5 times of set points. Setting the CT primary is like programming a current converter app. If you are in a foreign country, you see a price of 5. The app needs to know the exchange rate to tell you actual cost is 300. Without entering the 300 exchange rate, you have no way to know if 5 is a bargain or a huge expense. In the context of the Easergy protection relay, 300 amp to 1 amp ratio identifies a specific configuration for conversion phase current transformers or CTs, where 300 is a rated primary current and 1 amp is a rated secondary current. To ensure the relay accurately reflects the state of the electrical networks, you must enter these values into the scaling view of the setup software or the CT-VT view on the local panel. The secondary wires from the CTs, typically marked S1 and S2, must be connected to the relay analog module in slot A, specifically terminals A9 through A18. It is crucial to never energize the primary circuit until the scaling settings are properly configured, as incorrect settings can lead to unaccepted operation and damage. The relay uses this ratio to perform internal maths to convert the low-level signals into received into primary network's values. With the 200:1 ratio, the relay applies a multiplier of 300. If the relay detects a secondary current of 0.5 amps at this terminal, it calculates the primary current as 250. For the relay maintain accuracy during the fault, the CT must be sized so it doesn't saturate in this. If you're using definite time protection, the CT saturation current must be greater than 1.5 times the set point to ensure the relay receives a clear signal to trip. Think of the 300:1 CTs like high-powered telescope. The primary current 300 is a massive distance planet you are looking at, while the secondary current 1 amp is a tiny image you see through the eyepiece. By setting the relay 200:1, you are telling the relay the magnification power of the telescope. Without this information, the relay may see 1 amp imagined and have no idea for looking at what. In the protection relay, CT secondary refers to the rate output signal from the current transformer CTs that is physically connected to the relay analog measurement terminals. This secondary signal is what the relay directly monitors and then scales to calculate actual primary networks. The P5 supports various secondary settings depending on the transformer type and the specific protection application. There's phase CTs. The rate secondary current is typically configured as 1 amp or 5 amp. Standard airfoil CTs, these support secondary ratings of 1 amp, 2 amp or 5 amp. Or very sensitive airfoil CTs, these are fixed at 1 amp secondary rating. Low power current transformers, these differ from conventional CTs by providing a voltage-based secondary signals specifically rated at 22.5 millivolts. Terminals and secondary wires, conventionally marked S1 and S2, are connected to relay slot A analog module. For modules using low power sensors, the secondary connection is made via standardized RJ45 connectors rather than screw terminals. It is recommended to use sheeted cable shields by tinned copper braid for core balance CTs. The relay analog inputs are designed to impose minimal burden load on the CT secondary circuit to maintain measurement accuracy. Conventional phase CT inputs have an independence of less than 0.02 ohms. The secondary inputs can handle a continuous current of 20 amps and a 1 second surge of 500 amps. Secondary scaling is the mathematical bridge the relay uses to understand the power system. The relay uses the enter CT's ratio to convert the terminal signals into primary amps. Most protection pickup thresholds are set as multiple of the rated secondary current, making the protection logic independent of the specific primary size of the transformers. You must never open circuit the secondary of live CTs. Doing so produces lethal high voltage and can destroy the installation. The secondary of the line CT must be short circuit before opening any connections to it during maintenance. And do not energize the primary circuits until the secondary scaling settings are properly configured in the relay, as this could cause unaccepted operation damage. Think of the CT secondary as the low volume setting on the massive PA system. The primary network current is like a concert deafening noise, while the CT secondary is the small manageable electrical signal sent through the wire to the mixing table. If you unplug the wire while the music is playing, the energy has nowhere to go and they cause an noxious pop. Phase CTs or phase current transformers. Polarity refers to the orientation of the current transformers relative to the direction of electrical power flow. In the P5, correct polarity is essential for relay to accurately calculate the power measurements and determine the direction of electrical faults. Physical wiring and identification. CTs are marked with the primary terminals, typically P1 and P2, and secondary terminals S1 or S2. On the P5, secondary CT wires are connected to the analog modules in the slot A, specifically terminals A9 through A18. If the secondary wires S1 and S2 are swapped at the relay terminals, the measurement current phase will not be shifted by exactly 180 degrees. The relay must be told which direction of the current flow should be considered positive. This is configured in the scaling view of the general menu using the direction parameter. When set to outgoing power supplies by the bus bar to the load is treated as a positive. Incoming feeder, when the incoming power supply to the bus bar is treated as positive. Incorrect polarity can lead to the two primary type of failures. Example 1. Directional protection failure. Direction protection stage determines if the fault is forward or reverse. If the CT polarity is reversed, the relay will be seen at forward fault as beginning in the reverse direction, and the direction phase over current function will not trip a fault on the line it's supposed to protect, but it might trip unnecessary for fault elsewhere in the system. Example 2. Incorrect power metering on an outgoing feeder. Current normally flows from the bus bar to the load. If the CT is wired with the reverse polarity, the relay will be calculated negative power. The HMI would show the feeder as generating power back in the substation, which would provide first data to the SCADA system. Because wiring errors are common, it's mandatory to verify polarity during commissioning. Think of CT polarity like one-way turnstile at the stadium. The turnstile is measured to count people entering to the building. If you install the turnstile backwards, it will be only let people leave, and the entrance counter will be either show a negative number or fail to register anything. In the P5 protection relay, the number of connected phases CTs also refers to the number of CTs is scaling parameter that defines whether the relay is monitoring current from the 2 or 3 physical current transformers. This technique is crucial because it tells the relay protectors which analog inputs to expect data from, which internal protection algorithms can be safely executed. You can convert this parameter in the scaling view of the general menu using CTVT view of the local panel. There are two primary selections. 3CT mode, this is the standard configuration where one current transformer is installed on each of the 3 phases. And 2CT mode, this is used in specific networks types where only 2 current transformers are installed. In this mode, the relay only uses measurement signal from phase 1 and 3. Choosing the number of connected CT is not just about measurement, it's directly impact of the relay protection capabilities. If you select 2CT mode, the following functions are automatically deactivated because they require all 3 phases currents to calculate balance and balance components. There is also negative sequences. This function is inhibited because it cannot accurately calculate the negative sequence components without L2 currents. Think of the number of connected phases CTs like eyes of the safety system. If you tell the system it has 3 eyes, it can use its depth perception to detect complex problems like phase unbalance. If you tell it that only have 2 eyes, it can still see the something it's coming, but it loses the ability to judge depth, and you have to check those 2 eyes more often because the system cannot longer tell if one of them have gone blind. In summary, we have covered some functions. By mastering these parameters, you can ensure that the device is not only accurate, but to facilitate your system. Core conclusions. Identification. Through the main location and sub-location settings, you establish the clear administrative addresses for the device, which is vital for both local mimic display and long-term documentation. Flexibility and safety. The mode of use allows you to move beyond standard protection into test and test block environments, enabling the verification of physical wiring and internal logic. Thirdly, the scaling bridge. Scaling is the necessity that allows the relay to translate secondary input signals into accurate primary values. Without the correct set of CTs and secondary ratio, the relay cannot provide meaningful metering band protection. Finally, we examine the critical nature of phase CT polarity and the number connected of CTs. Incorrect polarity renders direction protection useless. While selecting DCT mode rather than CT mode automatically deactivates essential balance. Configuring P5 is like calibrating a high precision medical monitor. The location data is the patient name and ward number. The mode of use is simulation mode for training staff. The cybersecurity is the hospital privacy protocol, and the scaling polarity is ensuring the sensors are plugged in the right way around and reading the correct units. If you mix up the scale or the detection of the pulse, the doctor will make the wrong diagnosis.